Good morning. Okay. Um, all right. Just a few reminders. Project 3 is up now. So the due date for this is in 1 week, but please just pick a 48-hour window of time to work on it. It's up to you when you want to pick this window. Um, do try to have it in within a week so the TAs can start grading them. If you think that you'll need more than a week for some reason, just let me know. We can try to extend that by a little bit. Um, Also, the homework 9 you should have in either today or soon. Homework 10, try to get in next week as well. And there'll be a regular lab on this Thursday as well. Okay. Yeah, feel free to ask any questions about logistics if you have any. Okay, so today we're going to keep talking about ANOVAs. This is our last class. Will be the last lecture in this sort of series of lectures when we've been talking about different kinds of classical statistical tests. And so we spent last class introducing this idea of ANOVA, these analysis of variance methods. And the main time we're going to use these is when we have one or more factors that have more than two levels in them, right? Which means that we have some kind of grouping variable, some kind of nominal grouping variable for our participants that has more than two groups in it. And so instead of doing something like the t-test where we just looked at a difference between two pairs of means for two groups, we can instead do this more general thing, which is to look to see how much of the variability in the data is related to these group labels. And so this approach can work with any number of groups, and it can even work with multiple factors at the same time. So if we have a factorial ANOVA, right, we can have multiple axes along which we group people, right? We might have multiple nominal measurements for each person, and we can look at the impact of each of these factors independently, as well as any interactions between the factors. Okay, so today's lecture is going to have two pretty separate parts. The first part is we're going to do just a very brief overview of some of the different kinds of ANOVAs that you might see or that you might want to use depending on which situation you're in. We're really just going to skim through these just to give you a sense of how you might approach different kinds of data sets. And then for the second half of the lecture, I'm going to talk about relationships between ANOVAs and regression. This topic is usually not part of an intro stats class, but and it's not really going to be super required for the stuff that you're doing. But I think that it's a helpful way to think about ANOVAs. This is the way that most like actual psych modeling works, is by thinking about things as regressions. And so hopefully this is helpful. If this last part is too confusing, you don't need to worry about it, but hopefully it'll help you have a better understanding of the way that we usually think about these kinds of models when we're actually doing research. Okay, so we're going to start with the first part, which is thinking about different variants of ANOVAs. So the ANOVA examples that we were talking about last week made this assumption of equal variance inside the groups, right? What this means is that within each of our groups, so all the people that are labeled with the same nominal level, we expect that inside each of those groups, the variance should be about the same. And we can definitely imagine situations where this is not true, right? I think there was an example in the lab last week, for example, where this was didn't look like it was true. And right, you could definitely imagine where certain groups might have more variability inside them than others. So for example, if we're comparing like a placebo group and a group that's getting some kind of drug, there might be a lot more variability in the drug group because people have different responses to the drug. So the basic kind of ANOVA, this might be too severe of an assumption violation. But there are other versions of ANOVA you can use. So for example, one of them is called Welch's ANOVA, which is basically like a regular one-way ANOVA, but can deal with this issue of different variances. And right, what it basically tries to do is groups that it thinks are more noisy will have less of an impact on your answer. And it does this by adjusting the effective degrees of freedom. So you don't have to know any of the math about how this works, but this might be an option that you could use in R, for example. And so ordinary ANOVAs are generally pretty robust against unequal variances. And so even if the variances look a little bit unequal, it's probably not that big of a deal. And so people will often choose to use an ordinary vanilla ANOVA if they can. One of the reasons for that is because this Welch's ANOVA does have a bit of a power decrement. So especially for small samples, your chance of getting a false negative is a lot higher, right? The chance of detecting a true effect, which is what our power efficiency is lower when we're switching to this Welch's ANOVA. So usually what people would do is maybe just using Welch's ANOVA all the time is a little too cautious, because you're going to always be paying this power penalty. So usually what people do is first look to see if their variances look about the same or not. And we only use this Welch's test if the variances are obviously different. So there's some like null hypothesis tests you can run to see if the variances are different. You could also just inspect them with your eyes. Remember that this assumption is about the variances in the population, which we don't know. And so really all we can do is look at the variance in our sample and see if it looks like we think there's an obvious variance difference across groups. And if so, then we can use this Welch's test. Now, one thing to note here is that this Welch's test still assumes that the residuals, meaning the within group distributions, are still normally distributed in the population. Right. So it doesn't deal with that assumption, but it does deal with this variance assumption. And so, yeah, so one rule of thumb, for example, is like if the group with the least variance, so the group that has the narrowest distribution, is at least as wide as like a third the size of the widest distribution or something like that, right? So if the ratio of variances looks like it's like less than 1 to 3 or something like that, then that's probably close enough that a regular ANOVA would be fine. If it looks like the population variances are farther apart than that, then you'd want to use one of these Welch ANOVA variants. So another way we can modify our basic ANOVA is by trying to deal with this assumption about normality within the groups, right? So another assumption that we're making with the basic ANOVA is that inside each group, the distributions are coming from a normally distributed population. And again, there's lots of cases where this might not be true. So for example, there's lots of kinds of diagnostic tests where a normal score is going to be close to 0. And there's going to be this very long tail of high scores for people. So these could be sort of like personality tests or medical diagnosis tests, right? You might have tests where you might have a type of memory test, for example, where we expect people to make very few errors, but people with a memory deficit might make a very large and unpredictably large amount of errors. And so we can make use of a trick that we used a few lectures ago, which is using a rank transformation, right? So anytime we have a really weird looking distribution, there's sort of a few ways to try to deal with it. So one is that if our data set is large enough, then sometimes that can be okay. That's actually doesn't really work for ANOVAs, but for tests that only depend on sampling distributions of the means, like a t-test, then having a big sample size by the central limit theorem will give you a normally distributed sampling of the means. Another approach is this rank transformation, right? That we're going to throw away the actual shape of the distribution. We're going to force our data to have this uniformly distributed rank distribution. Another approach is to just use a more brute force approach, like permutations and simulations and things like that, to figure out what the null hypothesis should look like for this weird distribution. Right. So one of these tricks, again, is this rank transformation one. The rank version of an ANOVA is called a Kruskal-Wallis test. And the steps of this we're going to go through in a second, right? But the The idea is that this is like the rank sum test that we talked about, but now we can have more than two groups. It's testing this null hypothesis that the groups have the same population medians. And so again, the exact shape of the distribution doesn't matter so much for the medians. And it's going to involve converting all of our measurements, all of our scale measurements into just ranks. And we're going to throw away the original data and just keep these ranks. And ranks are guaranteed to be nicely behaved, right? They're guaranteed to be uniformly distributed. And so the nice thing here is that the null hypothesis is really simple because we know exactly what the mean and variance of our distribution is, because it's just this uniform rank distribution. And we're going to do something similar to an ANOVA. We'll go through in a second that, right, we're going to get a critical value saying the extent to which we think that there's more, the extent to which we're reducing our variance by knowing the group labels, right? So are the rank distributions inside each of the groups, do they have lower variance than this overall sort of starting distribution of all ranks? Okay, let's review those two things we just talked about with a quick quiz, right? So we just talked about first the Welch's ANOVA and the Kruskal-Wallis ANOVA. What two problems do these things deal with? Unequal group variances and non-normal groups and unequal group variances, right? I'm asking which one is which. Non-normal groups and unequal group variances, or group sizes and small group sizes. Okay. Okay, so what can these help us deal with? Yeah, that's right. The answer is A here, right? So Welch's ANOVA is the one that deals with unequal group variances, right? Meaning that inside each of the groups, they might have different variances. Kruskal-Wallis is the one that can deal with non-normal groups by just taking this rank transformation, so we don't have to deal with a potentially very skewed, for example, or bimodal or something distribution. Yeah, none of the things we've talked about really deal with having very small groups, although ANOVAs can be pretty robust even to pretty relatively small groups. Unequal group sizes is not a problem, even just for basic vanilla ANOVA. In R, you can use unequal group sizes. The way it figures out the degrees of freedom is a little complicated, but again, R can just do that for you. Okay, so let's go through an actual worked example of this Kruskal-Wallis test. So here are the steps to run this. And again, this is the rank transform ANOVA test. So we start by rank transforming all of the data, right? What that means is we ignore the group labels for a second and just sort our data from lowest to highest and assign ranks. And again, at this point, we throw away the original data. We're just going to use these ranks. Then the statistic we're going to compute here is we're going to figure out how many groups are in each, how many subjects are in each group. And we're also going to sum up the sum of the ranks inside each group, right? So if we have our k different groups, we have maybe k different levels of this one-way factor. Then we can compute what's the sum of the ranks inside each group and how many subjects are there inside each group. And then we're going to compute this sum between group sum of squares using this formula. Right. Again, the like math details are not so important here, right? But right, this formula is making use of these two things we computed, which is how big are each of these groups and what's the sum of the ranks inside this group. And you can see here that this SS between, we don't actually need to compute like a SS within here because the ranks are guaranteed to be uniformly distributed between 1 and n. And so we can actually just like subtract off this constant value here. Right, so this cross walls test is a little bit simpler than the regular ANOVA in the sense that we know exactly what the variance is of the whole group because we've forced it to have this uniform rank distribution. So we can just use this formula here. Again, we compute this SS between, plug it into this formula, and it'll give us this H statistic, which is kind of like the F ratio, right? But this is now this rank version. And again, we're going to compare H to some critical value. And the degrees of freedom here, just like in the regular one-way ANOVA, is the number of levels -1. Right, so again, I'm not really going to go through where the numbers in here come from. You can see there's like a weird 12 that appears, which again has to do with the variance of a uniform 0-1 distribution. But right, the only things you need to plug in here is the total number of subjects n, the number of subjects in each group, and the sum of the ranks inside each group. So here's some data we were looking at last time. This is just toy data from 3 different groups. So right, the first step we would do is rank all of these points from smallest to largest, right? So this point down here would be rank number 1. This one over here maybe is, it would be rank n. And so once we've ranked all these, we can sum up our ranks inside these groups. Here, all the groups have the same size. We can sum up the ranks inside them. You can see that the blue group here has the smallest sum of ranks because its points tend to be smaller than the other ones. Then we just plug in our formulas from the previous slide. So we're summing up t squared divided by n for each of these groups, subtracting off our constant, and then plugging into our h formula. We end up with this 17.71. Right, so this is our statistic in our data. This tells us that, right, and the null hypothesis here is again going to be that h is like around 1. And so here, this is a lot larger than 1, and it's specifically, it's larger than the critical value for 2 degrees of freedom, right? So what this is saying is that for 3 groups, we reject the null hypothesis anytime h gets above 6, and we're very well above that here, right? So that would tell us that it's not like there's some impact of group here. Just like in the regular ANOVA, it doesn't actually tell us which groups are different from which other ones. We're going to talk about that on Thursday. But it does at least tell us that there's something going on, right? The colors here are related to this scale score we're getting in some way. And here this is not telling us anything about the actual values here, just about the relative ranks, right? It's telling us that the ranks of our points are related to these group colorings in some way. Just to quickly run through what the assumptions of this test are. We're assuming that these points are random uniform samples. They don't have to be scale data, but they have to be at least ordinal so that we can rank them. They could be scale data. We're assuming that the groups don't have any errors in them. For this particular math to work, the data have to not have ties. If you're using this in R or something, it can deal with ties, but it can't use these formulas. And really the main thing this buys us is this assumption here, which is that we don't need the groups to have normal distributions anymore. We do need the variance to be roughly similar across the groups. Or I should say the distributions have to be roughly similar across the groups, but they don't have to be normally distributed. And so, right, since we're throwing away the exact scale data, just using the ranks, we don't actually need the data. We can get rid of this normality assumption. It is worth noting here, though, right, we still have this issue about the variances being homogeneous, right? So what this means, the variance constraint here is on the ranks, that the variation in the ranks needs to be similar across the groups. And so, right, we talked first about the Welch's ANOVA that can deal with different variances in the groups, but the groups have to be normal. We talked about this Kruskal-Wallis where the groups don't have to be normal, but they do have to have similar variances. And unfortunately, if both of those assumptions are a problem, then there isn't really any good classical test we can use. So if you have groups that are both non-normal and have different variances, there isn't really a good classical test. Again, you can always use things like permutation tests, right, where we just shuffle up the group labels and make our own null distribution. But there isn't like a standard like F or H or something distribution. We'd have to make our own distribution for what this looks like for this particular sample. I mean, of course, there is just a practical problem here that if the groups are really wildly inconsistent, then testing whether their means or their medians are the same maybe is not a super useful thing to know. If their distributions are very complicated, then a simple test of central tendency might not actually tell you that much. But yeah, so if our data breaks enough of these assumptions, right, we're going to have to create our own sampling distribution by permuting the group labels, for example. Okay, so to sum up this section, right, when we're looking at our data and we're hoping to run some kind of comparison between groups, right, the first question we want to know is whether our populations seem normal. And again, we can't actually know this from looking at a sample, but we could make some guess about whether it's plausible that these populations are normal or not. So for example, we would expect that we want the groups to be sort of roughly symmetrical around their mean. They shouldn't have huge outliers. They shouldn't have like multiple modes that are far apart from each other. If these groups are not normally distributed, we'd have to use some kind of rank test, right? We could use a rank sum test for two groups. We could use this Kruskal-Wallis test for more than two groups. That will get rid of whatever weirdness is happening in this population by forcing the distribution to be these uniformly distributed ranks. Or we could, again, fall back to our more brute force kind of permutation tests, for example, to just compute a null sampling distribution from scratch. Another thing we need to check is whether the variance in these groups is uniform. And again, this is a question about whether the population variance is the same, which we can't know from looking at the data, but we can make a guess. And so, right, the ANOVA is generally robust against this. And so it's usually not a huge deal, although you should definitely check. And again, a sort of rough guideline is that you don't want the variances to differ by more than a factor of 3 across any of the groups. If it looks like the populations do have wildly different variances, then you could either use one of these Welch's tests, either the Welch's t-test for two groups or this Welch's ANOVA for more than two groups. And those tests will basically make adjustments to the degrees of freedom to try to deal with the fact that you have these different variance groups. Or again, we can always fall back on these brute force permutation methods to just compute our own sampling distribution. Okay, we'll do a quiz to sum up things in this section. Also, again, if you have any other questions at any time, feel free to ask. Okay, and so the question is, what kind of test could we use if we have non-normal groups, right? So the distributions that are inside our groups are not normal. Let's see, hopefully this is still streaming. Okay, there we go. Okay, so what kind of test can we use with non-normal groups? A is Kruskal-Wallis, regardless of the group variances. So we could always use Kruskal-Wallis. B is we could use Kruskal-Wallis, but only if the group variances are similar. C, we could use a permutation test, so shuffle up the group labels many times to make a null distribution. Or D is that we could do either B or C. Okay, so what kind of approach could we use for groups that are not normally distributed within the groups? Great, seeing a lot of D's, which is the correct answer, right? That we could use the Kruskal-Wallis test as long as the group variances are similar. And permutation tests is almost always an answer, at least for the kinds of models we're talking about in this class. You can almost always just fall back on the stuff we did near the beginning of the class and just create our own sampling distributions and forget trying to actually fit this into a standard F distribution or H distribution. Okay. Um, so there's one more type of ANOVA in the ANOVA zoo that is important to know, which is referred to as repeated measures ANOVA. And the idea here is that we might run a within subjects test. So remember, with our t-tests, we had our independent samples t-test where we had two totally separate groups of people and we wanted to compare their means. But we also had this paired t-test where we got multiple measurements within the same person and wanted to run some kind of test on the differences within each person. So for example, you can imagine a drug study where maybe we want to know what the right dosage of a drug is. And so instead of having independent groups of people take different doses, we could give different doses to the same person. We'd want to like space these out in time probably and make sure we randomize the order and things like that. And the nice thing about doing an experiment this way is that we could account for individual subject differences, right? So maybe there's some subjects whose condition is way worse than others, for example. And so by just measuring these differences, the hope is that we can isolate what's going on with the drug specifically, that we don't necessarily care about these these baseline differences between people, right? So the fact that some people start out with a more serious condition than others, for example, that kind of variance is not relevant to the drug question that we're asking. And so, right, so we might want to conduct an experiment like this if we can. And so now we have this data set where every data point is labeled both with the subject as well as the dose. And the sort of weird thing here is that we have exactly one data point per condition combination, right? So if we have 10 different subjects and we give 3 different doses to each of them, then we have these 30 different outcomes, right? How well these 10 subjects did at these 3 different doses. And then we just have a single number for each of those 30 combinations. Yeah, so there's the question here too about we might want to test how different subjects are, which is true, and we're gonna talk in a second about how we might test how if the drug has different effects in different people, for example. This kind of a test is not relevant just for asking about baseline differences among people, although we might be interested in that too, right? Just to know how much we could just look at like variance in the placebo group or something. Okay, so we have this data where we have 2 factors sort of, but one of the factors is which subject this is from. The other factor is the dose. And so if we try to use our usual, our like 2-way ANOVA diagram from last Thursday, we're in this sort of weird condition where there's 0 error. There's this SS error term is 0 because there's only exactly one data point from every subject. Every combination of subjects and doses just has a single data point. And so we can't actually, there's 0 within group variation here because each group is just a single data point. And so in this repeated measures ANOVA, this SS error term doesn't exist. But we do still have these other 3 terms, right? We have this SS subject, which is telling us something about variability across subjects. We have SS dose, which is telling us something about the impact of the drug, and this SS interaction term, which is all the nonlinear relationships between subjects and dose. And so the way we compute an F ratio here is actually we look at the variation in the data that's related to the dose divided by this variation related to the interaction term, right? So we're dividing this green thing by this blue thing here. Right, in a regular 2-way ANOVA, we would be dividing any of these 3 things by this SS error term. Here, the denominator is now this different thing, this mean squares interaction. And so this is kind of weird, right? We're sort of treating the interaction term like it's the noise baseline, at least relative to what we did last time. And the intuition here is that in a repeated measures design, this interaction is actually the more logical kind of noise, because what we're testing with a repeated measures design, and this was true for our paired t-test as well, is we're testing whether there's some kind of additive effect of the drug, right? That what's going to happen in a sort of perfect scenario where our model is perfectly descriptive of the data, what's going to happen is that when we increase someone's dosage by a certain amount, that's going to cause every single subject to have the same change in their outcome. And so basically what we're testing here is we're asking, to what extent is there a main effect of the dose, meaning that there's some additive effect of the dose that's consistent across everyone, versus an interaction term, which means that every subject is responding differently to this drug. And that's a bad thing for this model, right? What we want is that there's going to be changing the dose of the drug is going to have the same additive effect on every person. People may start at different baselines, right? But the amount of improvement or amount of decrement that they're getting from this drug is going to be the same across people, right? And so this kind of F-score we're computing here is asking the extent to which subjects are responding the same way to the drug or not. It's asking to what extent is there just a drug-related additive effect versus some kind of person-specific drug interaction, right? Again, what we'd want to see is that this term on the top is big and this one on the bottom is small, meaning that there's a very predictable additive effect of this drug. If there's some kind of complicated interaction, right, what that means is that it's going to be hard for us to predict whether this drug would actually help or hurt in some new population. So repeated measures ANOVAs have basically the same assumptions as factorial ANOVAs, except that now our observations are not all independent, right? So we're getting multiple measurements from the same subjects here. And so instead, the assumption here is that different subjects are random independent samples from the pool of all subjects. But we're not assuming that measurements within a subject are going to be independent. And in fact, they're not going to be independent, right? And that's the part of the point of this is that someone's outcome after they get the drug is going to be very highly correlated to their baseline condition before they got the drug, right? If someone starts out very sick, for example, and they get the drug, they may improve, for example, but they're probably still going to be sick after they get the drug, right? And so the point of these repeated measures ANOVAs is that we can try to remove that baseline subject variance, right? What we want to figure out is how much of this outcome is related to just the placebo measurement for this person, for example, or their baseline measurement, and how much of it is related to the drug, right? So the assumptions here are different, that it's okay to have this within person correlation, but we do want the subjects we're getting to be independent random samples. There's another assumption here, which is sometimes a bit of a problem, which is has this fancy name of sphericity, which is basically just a sort of homogeneity of variance thing, but instead of being on the raw data, it's on these different scores between the levels, right? So what this says is that if you take every pair of conditions here, so like 5 milligrams versus placebo and 10 milligrams versus 5 and 10 milligrams versus placebo, for all of those differences, you need to have the same variance of those different scores. And so this is a pretty strict assumption, right? There might be, there could be many of these pairs if you have a lot of levels. And so for this to hold for every single pair might get kind of unreasonable if there's lots of levels. There are ways to deal with this. There are like these complicated procedures that can try to figure out how to adjust your degrees of freedom, which we're not going to talk about. But so there are ways to deal with this. Again, this is an assumption that you'd have to check to see if it's plausible that are all of these differences coming from a population with the same variance. And if they're not, then you can either use these kinds of correction techniques, or there's even like non-ANOVA ways of trying to deal with this. Okay, so to sum up this repeated measures ANOVA part, in which of these situations would a repeated measures ANOVA be valid to use? A is comparing results from multiple political pollsters. B, a longitudinal study of aging adults. C, comparing outcomes of different drugs that are given to different people. Or D, identifying bad data that should be remeasured. Okay, so which of these studies would meet the conditions that would make a repeated measures ANOVA potentially useful? Right, I'm seeing B's, which is correct. Right, a longitudinal study means that we get multiple measurements from the same person over time. That's the repeated in repeated measures, is that we're repeatedly measuring the same people. Examples like A and C, which are comparisons between different groups of people, that would just be a regular ANOVA, right? We're not getting multiple samples from the same people in those cases. Okay, so to summarize the first half of this lecture, right, the sort of full menu of ANOVAs that we have is if we have a single factor, we could use a one-way ANOVA. If we have multiple factors, we could use a factorial ANOVA, which could be two-way, three-way, or more. If we have different variances, different population variances in different groups, we could use a Welch's ANOVA. If we have non-normally distributed groups, we could use a Kruskal-Wallis rank version of ANOVA. If we have multiple measures for each person, we could use a repeated measures ANOVA. And this is really only like a very small number of the kinds of ANOVAs people use. For example, there's another commonly used ANOVA that we're not going to talk about, which is called an ANCOVA, which is where we, in addition to measuring the thing we care about, we're also measuring things that we don't care about. And we want to use those as things we're controlling for, right? So maybe what we want to know is we already know there's some impact on people's outcomes based on their socioeconomic status. And that's not what we are trying to study with the drug. And so we might try to control for that, right? So asking beyond this thing we already know about, the socioeconomic status, is there any additional impact of the drug? And so, yeah, people have built up a big library of these different kinds of tools. R can do many of these things for you. To some extent, it can also, there's packages that will try to automatically detect which of these is relevant for your data, right? Which assumptions have been violated in your data. Okay. So we're going to, for the rest of the lecture, we're going to move on to this different topic about regression. So are there any other questions on this first half? Okay. All right. So what we're going to talk about for the rest of class is another way to think about ANOVAs, which at least for me is an easier way to think about them and is usually the way that people do think about these kinds of models in the literature, because this way of thinking about them is actually way easier to extend to more complicated kinds of models. And so the idea is we can think about an ANOVA as a model that's essentially a linear regression, but instead of having a continuous input feature, which is right, a continuous x value like we talked about in the past, instead we have discrete nominal features. And so again, this is often the way that we actually think about these kinds of models. The actual like statistics here is identical to what we've been talking about. This is just a different way of writing ANOVAs. And again, I think it's potentially an easier way to think about what ANOVAs are doing. So let's think about the gender dose example from the last lecture, where we have right, where we have a bunch of people. We're looking at some kind of medical outcome, and for each person, we know both their gender as well as which dose of the drug they were put on. And remember, this is like in a cross subjects design, right? Each person is just getting put on one dosage of the drug. And the idea with a regression, remember, is that we're going to take some kind of feature about our person, about this particular person, and then try to predict what their outcome is going to be. So we could start with just a sort of like the very simplest model, which is like a zero-way ANOVA, where we don't use any information about each individual person. All we do is any person that comes into our clinic, we just predict the average outcome for them, right? This is like the easiest kind of prediction to make. We don't use any information about the person. We just predict that they're going to have an average outcome. And so our prediction model would look sort of like this, right? So yi is the actual outcome for this person. This is their actual outcome. And here is our prediction for this person, which is we're just going to predict the mean outcome for everyone. And then this plus epsilon is soaking up all of the mistakes that we're making, right? So each person's actual outcome is equal to our prediction plus how wrong we were for this particular person. So if we think about our ANOVA equations, right, if we want to compute this mean squared error term in our ANOVA equation, what we want to do is get the sum of squares of our errors divided by the degrees of freedom. And so the error term here, right, is just these little epsilons. These are the residuals of our prediction. And the degrees of freedom here is just n minus 1. And so these epsilons here is basically just saying our prediction is we're predicting that you have a mean outcome, and this is your actual prediction. And so the amount of mistake we're making is people's actual outcome minus what we predicted, which is the mean. And this formula here is just exactly the formula for variances, right, with this n minus 1 population correction. So in this case, where we just have this super simple model where we just predict the mean for everyone, there's just like one ANOVA term we can calculate, which is this mean squared error term. And this is exactly equal to just the variance of y, right? So what's happening here is that the total amount of variance in the data here is just entirely in this error term. We're not predicting any variance because we're just predicting the mean. So if you think of like our ANOVA circle, the circle is just entirely MS error, right? It's just entirely these sum of squared errors. There's nothing, we're not predicting any variance with this model. Okay, so let's try to make our model a little smarter. So we could think about a one-way ANOVA as corresponding to a model where we get to use one piece of information about our subjects. And so, for example, a one-way ANOVA we could construct here would be that we know which doses of the drug this person was put on. So someone comes into the clinic, we know that they are either on placebo or 1 milligram or 10 milligram. And so what we're allowed to do now is we can adjust our prediction based on which group this person is in. So what we're saying here is that our prediction for this person is we're going to start out by predicting the mean. That's just kind of our baseline. And then we can add either one of three numbers to this person's prediction, right? So these betas here are just numbers that they're kind of like, I'm writing beta here. They're kind of similar to the betas that we'd use in like a multiple regression. But the idea here is that we just have these three numbers. So maybe what we're going to do here is that we have some overall mean, and people that are in the placebo group, we're going to guess that we're going to make our prediction a little bit lower for their outcome. This beta maybe is like -5 or something. We're going to predict that their outcomes are going to be a little bit worse than average. Maybe the people in the 1 milligram group are going to have about average outcomes, and the people in the 10 milligram group are going to have the best outcomes or something. Right? It also doesn't have to be ordered like that. Maybe the 1 milligram group is going to be the best. And so this would be some big positive number that if someone comes in and they're on 1 milligram of the drug, we're going to increase our prediction. Right? So what we get to do now is this is kind of like a regression model, right? But we're not like doing any multiplication here. This is just, we're going to adjust our prediction up or down by these betas, depending on which group you're in. And so, right, so the full model here is that people's actual outcome is equal to our prediction, which is the mean adjusted by some group specific adjustment. And then all our mistakes are just pooling up in here. So if we go to compute an F score for this ANOVA, right, one thing we need to know is the mean square computation for our drug, the drug factor, which is just the sum of squares of the drug divided by degrees of freedom. And so remember, the sum of squares, this is a between group sum of squares measure. And so if you look back to the formulas for this, right, what we're doing is this between group sum of squares measure is asking how different the mean of our group is minus the overall mean, right? This is like our grand mean, and this is asking how different the means of our groups are. And the key idea here is that the right setting of these betas is exactly this difference here. That and oh, actually I forgot a squared here. There should be a squared on this term as well, right? So if our placebo group, for example, if the mean in our outcome in our placebo group is less than the overall grand mean by 5 or 10 or something, we should set our beta to that same value. And so, right, what this tells us is that the sum of squares based on the drug outcome is actually just the sum of these squared betas in our model here. Right, so if our placebo group is doing worse by some amount, we'd want to set our beta to however much worse people are doing on average in the placebo group. Right, we're just using these betas so that we can modify our grand mean, and we can now instead make a prediction based on the individual group means. Right, these betas are basically adjusting our grand mean prediction, so now it can be group specific. And yeah, the degrees of freedom here are the number of levels, which is 3 minus 1. Right, and this is again just the formula from before, except I forgot a squared here. So draw that in. Okay. Right, so here's our MS. This is our MS drug equation. Our mean squared error equation is basically the same as last time, where it's just the sum of these errors. Except that the degrees of freedom here is slightly different, just because we sort of used up some of the degrees of freedom over here. And so our F-score for an ANOVA is this mean squares for our drug effect divided by the mean squares for our error. So again, if you look at the actual terms here, right, this mean squares drug is basically the sum of the squares of our betas, and this mean squared error is the sum of the squares of our residuals across subjects. Right, so what this F ratio is doing is it's comparing in this model what's the size of this adjustment versus the size of all these residuals. Right, what our F ratio is telling us is in this model, which is playing a more important role? Are these adjustments really useful and important? Or is really the main part of this model just these residuals, meaning we're just making lots of mistakes, and the mistakes here are really the main thing that's letting us actually get these YIs, right, is we have to do all these subject specific adjustments, right? And so what we're comparing is, did we actually get some big betas here? Are we actually able to make useful adjustments to our prediction based on which group people are in? Right, if the drug is having no effect, then all of these betas are going to be close to 0, right? We're not going to, if someone comes in and they tell us which drug group they are in, it's going to have very little impact on our prediction about their outcomes. And that means that these adjustments are going to be small. If there's a very big difference between the groups, right, this drug has a really big impact on outcomes, then knowing which drug group someone is in is going to lead to a big adjustment in our prediction of their outcome, right? And so that would give us a big F score because these betas, our terms are going to be big and our mistakes are going to be small. Okay. So we can then start making this model more complicated, right? So let's imagine now we're going to do a two-way ANOVA with just main effects, no interaction term yet. And so our two-way ANOVA here is that now we know for each person that comes into the clinic, we know both which drug group they're in as well as their gender. And so what we can do now when we make our prediction, we can start with just predicting the overall mean. Then we're going to make some additive adjustment that's based on their dosage. Then we're going to make some additive adjustment based on their gender. And any mistakes that we're making are just getting shoved into this term here. And so now our prediction, right, we're making two different additions. We're making a drug-related addition and then a gender-related addition. And so if we think about computing F scores here, we have these mean squared drug term, which is the same as on the last slide. And we also can compute a mean squares gender term, which similarly, the amount of variance that's related to gender is going to be related to the squares of these adjustment factors, right? If we know someone's gender and that makes a big difference in our guess about their outcome, then that means there's a lot of variance in this data set related to gender. We have the mean squared error term, which again is similar here. And then we can compute these two different F scores. And just like in the one-way ANOVA here, right, these F scores are basically telling us how big these adjustment terms are. So, right, this F drug is the same as on the last slide. It's asking how big are the drug-related adjustments relative to our mistakes. And now we have also this gender F score. How big are our gender-related adjustments relative to these mistakes, right? And so if knowing this some nominal factor about a person has a big impact on on our prediction about their outcomes, then that's going to lead to these big adjustments in our model. Okay, so we can also keep adding stuff into this model. So I'll do just one more slide of this stuff here, right? We could also think about adding in interactions. And so adding in interactions, this formula starts getting kind of large, but it's still the same idea, right? So this kind of model here is we know both people's drug group and their gender. And so our model is we start with some overall prediction, some grand mean prediction. We make a dose-related adjustment. We make a gender adjustment. And then we're also allowed to make some kind of dose gender interaction adjustment, right? So without this last term, we can have some dose-related adjustment and some gender-related one, but we can't say something about specific combinations, right? So maybe for this particular drug, for example, it only works if you give 10 milligrams to male subjects, for example, right? Everyone else has bad outcomes. The only group of people out of these 6 different groups is the 10 milligram male group. That kind of outcome would be really hard to deal with these first 2 factors, right? Because it's hard to have like a 10 milligram adjustment without knowing someone's gender. Similarly, it's hard to have a gender adjustment without knowing their dose, right? But this interaction term can deal with this, right? We can get to make a different adjustment to every single one of these 6 groups here. And so our MS interaction term, again, is basically just summing up the squares of these things here in this last term. And so now we have this other F-score, which is basically asking, is it helpful to do these interaction adjustments? Is it helpful to, after we've made, right, we've already gotten to make a drug adjustment, we already got to make a gender adjustment. Is it helpful to make some kind of combo drug gender adjustment on top of that, right? If we already have these first 2 main effects, are these betas out here different from 0 or not, right? That's what this F-score is testing. Is it useful to adjust our predictions based on this combination feature or not? Right, so here's our sort of full 2-way ANOVA with both main effects and interactions, right? And it's basically a prediction model where we can use information about the drug someone's on, we can use information about their gender, and we could potentially use information about both if it's useful. And then what we're measuring is whether the sizes of these adjustments to our predictions, how big they are relative to the residual error, right? And the residual error here is the differences across people that we're not able to predict by knowing just their gender and the drug. Okay, so let's stop there for a second. Again, feel free to ask any questions if you have them. So, right, when we're thinking about this regression framework, when we're trying to predict people's outcomes based on some factor about them, right? So we've measured some nominal factor about these people, and we're making predictions. The question is, what will give us a big F-score for this factor, meaning that factor is important? Is it when the corresponding adjustment for that factor is big, when the adjustment is small, when our errors are big, or when the mean is large? Okay, so what do we think? Right, I'm seeing A's, which is correct, right? So in this regression model, having a big beta coefficient means that when we know this factor, we're going to make a big correction to our prediction, right? We know, oh, you're someone in that group. That means that we have some big update to our prediction, right? The size of the mean here is not relevant to anything. That's just sort of a overall baseline shift. And B and C are things that will make our F-score lower, right? If our adjustment for a factor is small, that means it's not that important. And if our errors are really big, that means that our this factor is not very useful for predicting people's outcomes. So the way we can write these kinds of models in R, and I think you already saw this in the last lab as well, is that the way we'd write down this full two-way ANOVA with interactions is like this, which is that we're predicting their outcomes Y as a function of the drug group that someone's in and the gender, and their gender they're reporting, and also potentially this interaction term. So this weird drug gender notation means all possible combinations of the drug and gender groups. And so the nice thing about writing models like this is that we can potentially write down really complicated models that aren't just simple factorial models anymore. So for example, maybe we know other stuff about people. So certainly in a medical context, we know tons of stuff about patients. And so maybe we also know that these people come from different hospitals, for example, and we think that which hospital you're in maybe changes the way that they assess your symptoms, or maybe some of them just have better outcomes than others. So you could think about writing models like this. So this would be a model that we're predicting people's outcomes based on main effects of drug and gender and hospital. And you could also write down more complicated things, right? Maybe we think that that male patients have a particularly bad outcome at some hospital or something, right? And so we could also write models like this, which is that people's outcome, in addition to sort of drug and gender and hospital main effects, there's also some hospital by gender interaction, right? There's some specific combination of being at this hospital and being this gender, which is going to have some impact on your outcomes. And there's sort of if we really have three factors like this, the biggest model we could write down would look something like this, which is these is main effects of drug, gender, and hospital. It's also all pairs of interactions between each of those pairs of factors. And then there's also finally this enormous three-way interaction thing, right? Which is that particular dosages at particular hospitals for particular genders have some kind of specific outcome. Right, and so you could see these things could get pretty large pretty quickly, and you could potentially have a prediction model that has lots of different terms in it that's trying to correct for different combinations of things that we know about these subjects. So you might think that we should just try to do this, right? If we know lots of information about the subjects in our study, we should maybe just try to throw all of it into some massive regression model that uses both main effects and every interaction effect we could think of. And this is certainly an option you could do, and in some ways, some sort of recent machine learning approaches do go down this path. But one problem here is our power, right? Our power to detect true effects. And you can think about math-wise, the problem here is that adding more and more factors means that we're slicing up our variance into tinier and tinier pieces. And so it makes it hard to actually detect real effects, right? That if you have a regression model with many, many terms in it, each individual term is probably not going to be super helpful because there's so many other terms that could sort of correct for it, even if you took it out. And so it makes it really hard to actually figure out which of these factors are having a meaningful impact on our predictions. Right. So if we add too many factors, it decreases our power, which again means that there's more of a chance of a false negative. We might miss real important things about factors because it's hard for us to actually pull apart the contribution of each of them. There's also this issue, which we talked about way back in lecture 10, which is that, and yeah, that's good prediction there about this overfitting. And so, it's a good prediction from Melissa there. So, there's even if some factor is not important in the population, it will always have some non-zero coefficient in this particular sample, right? The betas that we're choosing they're never going to be exactly zero. We're always going to make some factor related adjustment. And so what that means is that putting in all these complex interaction terms, they'll have some kind of betas that are not zero, but it's hard to know if they're really useful or not. Another issue with ANOVAs in particular is that ANOVAs have a lot of assumptions in them, right? They have these assumptions they're basically the same assumptions as regression, which makes sense because as we're seeing here, they basically are regression. And so, for example, right, we don't want if some of the factors are really correlated with each other, we're going to have trouble actually figuring out which of them is driving effects. So yeah, what we'd like to do, ideally we'd have some kind of hypothesis about which features are important. I'm going to talk at the end of lecture 2 about some kind of approaches for this. So another thing we can do with this new regression way of thinking about ANOVAs is that we could think about including both continuous and discrete features into our analyses, right? So imagine that in addition to dose and hospital and gender and these kinds of nominal factors, we also know some continuous valued things about these subjects, like their age. And we'd like to make some kind of adjustment to our prediction of these people's outcomes based on their age. And so ANOVAs can't really handle this, right? ANOVAs assume that people are in these nominal discrete groups. But in this regression land, this is really easy to write down, right? All we have to do here is, so for example, if we want to use both people's drug group as well as their age as a continuous predictor, we can just write down this regression equation, which is that we're starting with this baseline prediction of the mean. We're going to make some adjustment based on drug group, and then we're going to make some adjustment based on your age, right? And this here is like a regular sort of slope times X regression, like we talked about when we first talked about linear regressions, right? Which basically, this beta here would basically say that for every extra year old someone is, we're going to make some adjustment to our prediction about their outcomes, right? We might predict that if you're an extra year older, we're going to predict that you're going to have slightly worse outcomes, right? Something like that. And the nice thing here when you're doing this in R is that you actually can write down this kind of model just like this, right? We just say our outcome is going to depend both on this nominal factor of drug as well as this continuous factor of age, right? And it internally figures out, okay, this is a nominal thing. That's going to mean we're going to do these like constant offsets. This is a continuous thing, so we're going to it's going to compute a slope internally. Right, so we can put in different features here. They can be now of different types. Some are nominal things, some are continuous things. We're going to try to use all of them to improve our predictions. So I'm going to run through an example of this and to try to give you some sense for like what these models look like. Again, it's not super, we're not going to ask you to construct models of this complexity, but maybe this gives you some sense for how we'd really construct these models and potentially use them, right, to actually make predictions. So this is a real data set about looking at the amount of vitamin A that is circulating in a person's bloodstream. So in this experiment, they took blood samples from people, measured how much vitamin A they had. And we also know some other things about them. We know, first of all, we have an estimate of how much vitamin A they're eating. So this is just an estimate, but based on, they had people keep diaries about what they're eating, and then they're making a rough estimate of their vitamin A consumption. And so this is a continuous scale variable. And we also know 2 nominal things about each person. We know whether or not they are a smoker, right? We have some threshold for what we consider calling someone a smoker. And they're also having people's reported gender. And so we can try to plot this data. It's a little bit complicated to plot, but here's one way to try to do it. So on the y-axis is the amount of vitamin A in their blood. This is a thing we're actually trying to predict. So it's on a scale from 0 to 500 nanograms per milliliter. And each dot here is a person, and you can see each dot has 3 different predictors associated with it. So each dot is somewhere on this vitamin A diet scale. And so that's this continuous one. And each dot here has a color, which says whether or not they're a smoker. And each dot here has a shape, which says their gender. Right, so you can see that this data is kind of, there's a lot going on in the data here, right? But there's a lot of there's variation among all of these different predictors. So let's say we want to construct a model where we're trying to predict what someone's level of vitamin A is based on these 3 things. And the reason we're doing this, one reason might be that we're just interested in which of these things matter, right? So we're going to run some hypothesis tests to see if these 3 factors, are they related to your bloodstream amount of vitamin A? There also might be practical reasons you do this, right? Getting blood samples from people is a pain, but getting them to answer these 3 questions might be pretty easy. So if we can build a good predictor, then we could estimate your vitamin A levels in your blood just by asking you these questions, and we don't have to get some kind of blood sample from you. Okay, so so the relatively simple model here would be trying to predict people's vitamin A levels based on whether or not they smoke. So in R, right, we'd write this as predicting vitamin A based on whether or not someone is a smoker. And if you use this linear model function, it'll pop out these two numbers. And so what these numbers mean is our prediction model is going to work like this. If someone comes in and we want to predict their vitamin A levels, first we start by just predicting 171 for every person. And if this person is a smoker, we're going to adjust our prediction down by 49. Right, so we could draw our model out, basically looks like this, which is that if you're a non-smoker, we're going to predict that your vitamin A levels are 171. If you are a smoker, we're going to subtract 49 from that prediction. Right, and so our predictions here they look like straight lines in this plot because they're not using this vitamin A diet thing, right? But if you are an orange dot, meaning you're not a smoker, we're going to predict 171. If you're a blue dot, we're going to adjust our prediction downward by 49. Right, so this 49 is like those betas I was showing earlier, right? This is saying that now that we know if you're a smoker or not, we either adjust, if you're not a smoker, we don't make any adjustment. That beta is just 0. If you are a smoker, we're going to adjust downward by 49. And then if we use our ANOVA command on this same model, it can tell us that this smoker adjustment is significant. Right, this adjustment of 49 is relatively big compared to the noise in the data. And so this is a significant, this knowing if someone's a smoker or not is a significant help in predicting their vitamin A levels, right? That's what this probability here is telling us, is that this is decreasing if we are able to know if you're a smoker, we're significantly decreasing the errors we're making. Also, just to point this out in case people are curious, so this smoker variable only has 2 levels. And so you could also run a t-test here instead of an ANOVA, and you get exactly the same answer. It turns out that, if you have data that satisfies both the ANOVA and the t-test assumptions, the t-score you get out is actually just the square root of the f-score, and the p-value here is totally the same. This is not that important, but just in this case, you could do this either way. Okay, now let's make our model more complicated. We're going to create a model here now that we're going to use both whether or not someone's a smoker as well as their gender to make a prediction about their vitamin A levels. So if we ask R to find these coefficients for us, it gives us this, right? Which is that we start with a baseline prediction of 175. If you're a smoker, we adjust that downward by 48. And if you're male, we adjust that downward by 32, right? So we're kind of using as like the baseline here are females that don't smoke. For them, we're predicting 175. If you smoke, we're going to subtract 48 from our prediction. If you're male, we're going to subtract 32. If you're both male and a smoker, we just subtract 30. You just get both penalties here, right? You get this smoking penalty and the male penalty. And so, right, so drawing this out here, right, you can see we're making 4 different predictions depending on the values of whether you smoke or not and what your gender is. But they're not really 4 like independent predictions, right? That the prediction for male and smoker is just the sum of the male adjustment and the smoker adjustment, right? So this is what we're saying here. This is 2 main effects without an interaction. What that means is that we just have these smoking related adjustments and these gender related adjustments. There's no combination adjustment. And so again, we can run an ANOVA here, and what that tells us is that the smoking seems useful, and gender is kind of borderline, right? It is helping, but it's not totally clear if it's helping more than even if gender was meaningless. Maybe you could have gotten the same f-score, right? This f-score is kind of borderline for the critical one, and so right, saying it looks like this f-score is helping. It's a little unclear if it's helping more than a null model would or not. Okay, so let's make this a little more complicated by adding a continuous predictor, right? So now what we're going to do is we're going to use both whether someone's a smoker or not and what their gender is, and we're going to ask them how much vitamin A they're getting in their diet. And remember, this is a continuous thing. And so now our model in R looks like this, which is that we're going to start out by predicting 140. There's a smoking penalty, there's a being male penalty, and then this here is a slope, right? Which says that for every unit of vitamin A in your diet, we're going to increase our prediction about your bloodstream vitamin A by 0.0159. right? So now our models kind of look like this. Right now we're tilting our predictions based on where you are in this vitamin A diet space, right? That's for every person. So our baseline prediction is like a female non-smoker that has zero vitamin A in her diet. We would predict 141 for her. And then, right, we can use this information to adjust that prediction, right? So the more vitamin A you have in your diet, the higher our prediction is going to be. If you're a smoker or a man, then we have these penalties that we apply, right? That we think your vitamin A is going to be lower. And if we run an ANOVA here, again, it can tell us which of these is important. And so it's telling us that this vitamin A in the diet is very important, right? This is actually the most significant factor, right? The most useful thing. If we can only ask them one thing, vitamin A in the diet is the most useful thing to ask them. Finally, I'm just going to make this one level more complicated, and then we'll be done with this example, which is that we could add an interaction term here. So here's a model where we have smoker, gender, vitamin A, and diet, and then we have a smoker, vitamin A, and diet interaction term. And what this means is that that we're going to use different vitamin A diet slopes depending on whether you're a smoker or not, right? So what this pops out here is if you're not a smoker, we're going to use this slope for you. And if you are a smoker, we're going to use this different slope for you. So now our model looks like this, right? Which is that we start with, our sort of baseline here is 132, right? And then if you're a smoker, then we actually give you a little bit of an increase, but for every extra unit of vitamin A in your diet, we're going to decrease our predictions, right? Whereas for the non-smokers, they're actually getting increasing predictions with more vitamin A. And right, if we do this ANOVA here, we actually get that this is significant, meaning that it's actually useful to have different slopes for the smokers and the non-smokers. I don't know like medically what's going on here, why this would be the case, right? But right, this is basically saying for smokers, and again, this is not a actually experimental study, it's just observational, right? But for some reason, these smokers that have a lot of vitamin A in their diet actually have less vitamin A in their bloodstream. Just to clarify, this last column here is literally just a p-value, right? What the notation here in the ANOVA table is the probability that our F-score is bigger than our critical F-score. And that's just the definition of what a p-value is, right? What's the probability that this F-score is bigger than what we would have expected from chance? So this last column here is our p-values for each of these four factors. So the probability that smoking helped our predictions was this. The probability that if smoking is not useful, we would have seen this level of effect is this, right? So what this is telling us is that if smoking had no impact on our predictions, it's very unlikely we would have gotten an F value this good, right? It seems like smoking is helping a lot here. The chance of getting of it helping this much in the sample and having no impact on the population is pretty small, right? So these are just our regular p-values. If this factor doesn't matter in the population, what's the chance we would have gotten these big F scores? Okay, so that wraps it up for that example. Right, and so just as a final quiz here, I showed a bunch of different kinds of models you could create. Which of these would be a valid linear model to write down? Right, I'm seeing D's, which are correct, right? We could use nominal values. We can combine nominal and continuous values. We could have interactions between any of the terms. We could interact nominal variables with nominal or continuous with nominal. You can't really have an interaction between continuous and continuous, or at least that takes us outside of the linear modeling framework, right? But any of these things here would be valid. Okay, so let me just finish up here in 1 or 2 more minutes. So, right, one question you mentioned is how do we actually pick which model to use for a data set? And ideally, we'd have some pre-existing kind of theory or hypothesis. But often the whole point of doing this experiment is we don't know what the right model is, right? And so how do we figure out what terms to put in our model? And so there's kind of two routes here. That the classic approach is what's called model comparison. So if we create two different models, we can actually, there's you can use an ANOVA to compare these two models, right? We're basically just checking whether, in this case, we're checking whether this extra term is significantly helping us or not, right? So we can, R can do this kind of model comparison. And here, for example, it's telling us that our errors are significantly lower if we add this extra term here. Another option, which we discussed earlier, is cross-validation, which means that we use some of our data to create this model and figure out the coefficients in our model, all those betas. And then we try to make predictions on a held out data set, right? And this is really the real test. If we actually want to use this model for prediction, this is really what we care about, is this kind of generalization performance to new data sets. And it's important that we really test on a new held out data, right? That's a new sample from our population. Okay, so to sum up, right, we talked about some variations of ANOVAs that let us deal with different kinds of assumptions, and also talked about this idea of thinking about ANOVAs and t-tests really as just special cases of linear regression, right? And again, this is usually the way we actually write down our models in psychology, is with these kinds of formulas that let us say, like, we're testing which of these predictors are related to some outcome. All right, any last questions? Okay, project 3 is up now. I also put up the solutions for last week's lab in case that's helpful for the project. We're having regular office hours this week. If you need help, you could also email us if you want to meet an additional time. All right, yeah, let me know if you encounter any problems with the project or if you need an extension. Great, see everyone soon.